Hi, everyone, and welcome to part two of multiple regression with interactions. We are going to pick up right where we left off, and we are going to look at collinearity, specifically variance inflation factors. This is something at the end of the script file in the last video set of videos. So here we see that variance inflation factors are quite large for most of these. There's kind of rules of thumb around what acceptable levels are, and they definitely exceed them. It's not super surprising to find this, as you would expect in an interaction, that an individual variable in that interaction is going to be related to something, the term of itself multiplied with something else. So it's common to get this. There are alternatives. So this is just one that you can look at, and here they don't look as bad. But we will come back to that in a second because we're going to talk about next. Centering or mean deviating is one way of alleviating or kind of addressing that collinearity issue that often arises when we're including an interaction or interactions in the model. So centering, and generally this approach I'm about to walk through, was proposed by Aiken and West, and you'll see the reference below. So here we're going to do it with our predictors, specifically x1 and x2. And as I'll note in a second, one reason for doing this is to have meaningful zero values. So we noted before that x3 is dichotomous, it's 0 and 1. So 0 is already something meaningful. Again, I'm not giving any sort of context, but 0 would be a category, right? Like if it was a gender category, it might be man or woman or something like that. So it already has a meaningful 0, but our x1 and x2 do not. So by centering, the 0 is going to be average. So I'm going to create two new variables here. I'm just adding the c so I know it's the centered version of x1 and x2. And you'll see that I'm just taking the values and then subtracting from the mean. So centering, this is one way of centering and called mean deviating, because we're turning all these values into deviations from the mean. And once we do this, you'll notice that in the data, it'll actually show 6 variables now because we just added 2 variables. And when we look at them, we did it right. You see, now the mean is 0 for both. So now let's run the model again, but with the centered x1 and x2. And then we can compare it to the previous model with uncentered variables. And I'm going to introduce briefly a new package. I already have it installed, but if you don't, you can install it right there. This is not a perfect illustration of the utility of this package, but wanted to introduce it at the very least. It might be handy to many of you when you want to compare several models in a nice table. Again, this is not a perfect illustration of it, but it is relatively easy to compare these two models now. You'll see in terms of centering, a basic thing to mention, things like r squared are not going to change when you center your variables. But some other key things that we can see in terms of differences between when we centered versus uncentered. First, here it says constant the intercept. So before, we didn't really have an intercept that we could interpret, because the intercept, remember, is the value of the dependent variable when the independent variables are all 0. x3 had a meaningful 0, but x1 and x2 did not. Now that we centered, this is meaningful. So this is the value of y when x1 and x2 are at their mean and x3 is at 0. So now the intercept is interpretable. It kind of means something to us. Another thing that we can see in terms of differences are the coefficients for x1 and x2. So before they're not significant, and here they are, and they're all over 1. Another reason that we can use centering, or why it's valuable, is now, again, kind of similar to how we can now interpret the intercept. It's easier to interpret these coefficients. And basically, we can interpret these coefficients as average effects. So that's another reason that centering is used. There's different ways to center things, and we'll be talking about centering going forward, but it is often used for similar reasons. For example, so that we can have some sort of meaningful interpretation. Now, quickly, we're going to check assumptions as I kind of put here. I say for kicks and giggles, because really my main point is to say that nothing is going to be different. So just because we centered doesn't mean that all of a sudden, we're going to have violated assumptions. So I'm just quickly running through this, but again, it wouldn't be actually necessary. And to illustrate how centering can help alleviate that issue of collinearity, if we look at variance inflation factors now, you'll see that they're all about 1. So at this point, typically we want to kind of probe and plot the interaction in some way. And there's several different ways to do this. I'm going to kind of run through some of the more common ways, but I really encourage you to kind of play around with some data and try maybe plotting in different ways, for example. So we're going to need a new package real quick, that SJ plot. So install that if you don't have it. One really common way, and it was proposed in Aiken and West to look at in interaction, is to fix the values of one variable to one standard deviation below the mean, and then one standard deviation above. So that's what we're going to do here. A visual inspection. So you'll see on the y-axis is our dependent variable. The x-axis we have x1, and then we have x2, negative 0.98, because that is one standard deviation below 0 and then one standard deviation above. Again, you can play around with this and do different things. I forgot to mention here that the type I'm saying interaction and then means SD. So that's how I'm getting that standard deviation below, then mean standard deviation above. And basically what this graph illustrates to us is that these the effects of the variables are kind of synergistic, or they increase the effects of one another. So as x1 increases, we see x2 increases pretty dramatically up here. Similarly, you could go the other way around as well. If we look at the slopes, it's a much stronger relationship between x1 and y when x2 is one standard deviation above the mean. Again, you're typically going to be treating one variable as the moderator. In this case, it doesn't really matter because it's hypothetical, but usually you have kind of one that you're treating as a moderator, or saying the effect of this one variable depends on the effect of this other variable. So in terms of kind of probing the interactions, there's two common ways. One is simple slopes, and the other one is marginal means. Again, lots of different ways to play around with both of these themselves. So we'll need a new package along the way. And we're going to start with simple slopes. So first, you'll see a common thing that we've gone back to before. So we're creating a new thing. I'm just calling it my list, and I'm saying it's equal to something. saying my list because it happens to be a list. Specifically here, what I want to do is get a list of values for x1. And specifically, I want it to go from -1 to 1 by 1, or in other words, from -1, 0 into 1. In this case, I'm doing that because -1 is 1 standard deviation below, and then 0 is the mean, and then 1 is 1 standard deviation above the mean. So I'm rotating those values first, just creating a list of that. Again, it'll pop up here on the right once you run that. And now I'm using this first, creating a new thing. You can call it whatever you want here. The EM trends, what we're going to do is grab the slopes or the coefficients of x2 at different values of x1. So that's what we're asking it to do here. You'll see at my list. So at the list I created up here. So the variable x2, I want those trends in that variable, the slopes or the coefficients, we could call them. And then here, that's what we get. So the coefficient corresponding to x2 when x1 is -1, it's 1.35. And then basically as x1 increases, x2 also increases. So we might interpret that, if it were appropriate with the design, that the effect of x2 is greatest when x1 is at a higher level, or a higher than average level. Again, you could rotate this around. So have different values of x2 over here, and then look at the coefficient for x1. So I'm just arbitrarily kind of choosing to do it this way. So it is possible to do t-tests to actually test to see if those simple slopes are different. There's some caution against that. Yeah, so I'll just leave it there. Maybe don't do that, but I'm going to show you how to do it, and you can kind of look into reasons for that. There's a good book on this that I'll put down there, a good general book, Cohen et al., that talks about this a little bit more. You can also Google for yourself. So I'll just show you how to do it, but maybe don't necessarily do these pairwise comparisons. Instead of simple slopes, or in addition to simple slopes, we can also look at the estimated marginal means. Similar type of approach here that you'll see. First, I'm creating this list. So now it's x1 and x2, and for both of them, I'm going 1 standard deviation below 0 and 1 standard deviation above. In this case, I'm using -1 because that's basically what they round to for both of them for these variables. But in your case, in your own data set, you'd have to do the specific value that is 1 standard deviation below and above. So first we create that list. Now you'll see we're doing means instead of trends, but similar command. Now we can look at them. So now we're looking, and I get the means at different levels of each. So 1 below for x2, 1 below for x1, x1 at the mean, x1 at 1 above. So we're getting a whole set of means. And we could plot these or do something else. Again, we can test these, maybe don't do that. But there's lots of different things that we could do. Or again, you can also kind of rotate things around depending on what you're focused on. But I hope this gave you kind of a helpful basic introduction to how you'd look at an interaction, specifically in this case, an interaction between continuous variables. But a lot of the principles are basically the same if you had one or more dichotomous variables included in that interaction. For example, instead of looking at the 1 standard deviation below the mean, 1 standard deviation above, you might do 0 and 1 when you're actually plotting and exploring the interaction. But otherwise, the steps would be very similar. So I hope this was helpful again, and I hope you stay tuned for future videos. Thank you for watching.